Hi, my name is Stefano Marchidis and I'm Associate Professor in High Performance Computing at KTH. I want to welcome you to the third cycle course called Introduction to High Performance Computing. And together with you, I would like also to go through a brief introduction to the materials and how the course is organized. So I already introduced myself. So I'm Stefano Marchidis and I will be the course responsible teacher and also the examiner. Together with me, there will be two assistants basically helping out us during the discussion of the assignment of the material. So we have Niklas Jansson and Artur Podobas as assistant to the course. So who are we? So basically, I'm leading the HPC group at KTH. So our area of research is the HPC, high performance computing in general. So to be more precise, what are the research topics we are working on? Well, we work on the message passing interface, MPI, that we're going to study in the third module of this course. We have a strong interest towards programming and understanding new technologies, especially when it comes to memories and storage technologies. We have part of our group working on how to do I/O and how to coordinate I/O in using parallel strategies. We have quite a lot of work on application side. So let's say that we want to parallelize an application. So which methods we can use, which methodology we can use, right? So myself, I'm a major developer of a particle in self simulator called EPIC3D. And also you saw Niklas is one of the main developer for NEC 5000, that is a computational fluid dynamics code. So we're also looking at how to deploy the parallel programming models in HPC application. And finally, we are also working on how to use and program accelerators. You might have heard graphical processing units, GPUs, and we will learn about them in the fourth module of this course. So what is this course is about? Well, this course is about making an effective use of the most powerful parallel computing system for problems in science and engineering. So when we do that, this requires us to pay attention to every part of the parallel system, from the small computing node to the network and what is on the computing node. It might be just a simple processor, it might be a GPU. It also requires a scientific and rigorous approach to performance, to have a performance expectation about our code, right? So we need to understand critically if the performance that we get is the one that we expect. So it might be that we get some performance, some execution time. How do we know that is a good performance time? So we will develop special tools and models to try to predict the performance of our code. So we have 5 course goals overall. So the first one is to understand the sources of performance in modern architecture, including GPU's architecture. So the major question here: how do you get the maximum performance given a certain CPU, certain GPU, or a certain supercomputer? We will also learn how to establish performance expectation, right? So expectation is different from prediction. So we are not going to talk about precise performance prediction, but instead basically have an estimate where our performance is going to be, and especially have an understanding that the performance that we're achieving is what we are expected to get, and if not, what we can do to achieve that. So we will learn how to diagnose performance problem, and we will also learn how to design algorithms and application to maximize the performance potential that is the given hardware in use, right? So it might be that in order to use a specific hardware, might be a CPU with many levels of caches or a GPU, we need to rearrange our code in order to use it. So there's also a part about algorithmic changes of the codes. And finally, we will see that in a supercomputer, parallelism is offered at different hierarchical levels. So we will learn how to address different parallelism level in our code. The intended learning outcomes for the course are the following. So by the end of the course, you will be able to describe and list HPC architecture's design choices and features. You will learn how to connect to a supercomputer, build and run codes on multi-core system and cluster on GPUs. You will be able to use HPC tools to measure and analyze the performance of computer codes running on supercomputers. And finally, you will be able to design, implement, and optimize parallel engineering application for HPC system using OpenMP, MPI, and CUDA. That are the three major approaches that we will learn during this course. What are the prerequisites to be successful in this course? Well, the first requirements, you do need a basic knowledge of the Linux operating system. And the reason for that is that the supercomputer have all a Linux operating system, right? So you might have a Windows machine to connect to the supercomputer, but once you're on the supercomputer via terminal, you will need to use the Linux command. So at least you need to know basic commands for copying files, moving files, create directory, and so on and so forth. You will also need a basic knowledge of C or C++ plus Fortran. So this is not a course about software design. So what we need is that you know all the basic understanding of C and C++. So I mentioned Fortran. Many of us still using Fortran. So please feel free to use Fortran instead of C. However, keep in mind that assignments are in C++, right? So the assignments are formulated in C++. So in order to submit the assignment in Fortran, you will need to write the small sample code that we wrote in C in Fortran. And also for programming GPU, the main approach is called CUDA, and CUDA is basically an extension of the C language. So it helps a lot to know C, so then can be used also for programming GPU. So basic knowledge of C++ is good. If you prefer Fortran, is also good to submit your assignment. However, keep in mind that some of the code that we provide are only in C, so you will need to work on the Fortran version. And finally, we ask you to have knowledge of command line editors like Emacs, VI, or Vim, because this is quite helpful when you work directly on a supercomputer. So the way that it works with a supercomputer, you connect from your laptop or your workstation to the supercomputer, and then you will have a terminal. And sometimes when you want to change your code directly on supercomputer, it's very useful to be able to use some editors that are from the command line. So if you want to still use IDEs like Eclipse, is still okay, but keep in mind that then you need to copy back and forth from the supercomputer to your laptop and vice versa. So also IDEs are okay, but then there's very little support for moving data, especially your code, to the supercomputer itself. So how the course is organized? So the course will consist of a series of different activities. The main one will be the online lectures. We will also provide some reading and some small quizzes. The course is organized in 4 modules. In the first one, we're going to look at performance modeling, benchmarking, and the computer architecture. In particular, we're looking at all those computer architecture aspects that impact the performance of our code. The second module is how to program shared memory programming, how to program shared memory system, where the shared memory system might be your laptop that is multi-core, so it has multiple cores in the processor and share memory. But also it can be the node of a supercomputer, right? So a supercomputer typically have 1 or 2 or 4 processor, each one consisting of multi-core that are sharing one memory. Right? So that is, we will learn how to use the multiple computing units from the cores of the processor that are sharing one main memory. And to do that, we are basically using OpenMP, that is a compiler technology. The third module is the one that is most relevant how to program a supercomputer. It's called Distributed Memory Programming with MPI. So we will learn how to move data from one computing node to the other computing node via the network. Right? That's why I say this is the most relevant to supercomputing. However, we can also use MPI on a simple laptop or on a workstation. Right? The fourth module is about accelerator, in particular graphical processing units, what they are good at and how do we use them in HPC. And also we will introduce how to program a GPU for HPC. As I mentioned, we will provide all the material. We will provide the material of the course via slides, together with the videos, and also articles to read, and some codes that you can just download from Canvas and try on your computer. So the lecture will be available online on YouTube and available in Canvas. So there will be 4 assignments with just pass or fail grade. So the first one is about HPC architecture, programming OpenMP, MPI, and finally GPU architecture. Each assignment consists of submission of a short document in PDF file where you're describing what you have been doing for the assignment, a submission of a GitHub repository with the code for the assignment, and so what you need to do. So the assignments are completed preferably in groups of 2 or 3 students. Also, if you want to do the assignment by yourself, is also okay. So you create a group by one person and then you submit it. But preferably, I think one of the goal of this course is also the collaboration with other people that might have different knowledge of computer science. So it would be good if you collaborate with other students for the assignment. However, if you prefer to be just by yourself, is also okay. What is important to notice that there is no penalty for working in a group of 2 or 3. Right? So at the same time, if you work by one, you won't be awarded. So how do you pass this course? Well, the way to pass this course is to complete the 4 assignments and pass them. So as soon as you finish all the assignment in a satisfactory way, we will pass the course. So if you want the credits to be registered, this year, make sure to submit all the assignments by October 23. That is the last day of the first period after before the P2 starts. So it's okay to submit late or a couple of days the homeworks. Try to have to read them and follow the schedule. However, if you want to get pass the whole course and get credits right away, please submit all the assignment by October 23rd. So you will be given access to the PDC supercomputers. So PDC is the High Performance Computing Center at the KTH. You will be given to 2 systems. So the first one is called Beskov, and is the largest one. However, it doesn't have any GPU that we can use for the 4th module of the course. So for this reason, also we are having access to other machine called Tegner that also has GPU. So we will be able to use GPUs. And also we will provide an allocation. We provide by email some instruction how to get allocation to the course. As a part of this course, you will learn how to connect and run jobs on a supercomputer. If you still haven't got an account on a PDC supercomputer or still need to start all the procedure, please try to apply it as soon as possible. Right? The first assignment can be also completed on your laptop or your workstation. However, it will be very good if you also get chances to access the supercomputer, and especially for the third module that is about MPI. So that will be extremely useful. The fourth module will require the usage of NVIDIA GPUs. So for that one, if you don't have an NVIDIA GPUs, you can use Tegner. But also keep in mind that all the computer science lab in the main campus at KTH, for instance, some of you know the green room, the red room, the brown room, they all have computers with NVIDIA GPU, so you can go to the lab and make your exercise there if needed. Anyway, we'll provide more information as soon as we start talking about GPUs. Let's talk about the course material and suggested textbooks. So textbooks in this course are not required. However, we will provide you some suggestion if you want to go deeper in certain aspects. So all the materials that I'm going to present in this course is a selection of the lecture for two of our courses at the master level, FDD3358, that is methods in high performance computing, and FDD2360, that is applied GPU programming. Right? So they talk about different topics, but I will use videos and slides from these two main courses. So don't be surprised if, for instance, in the video you see that I mentioned DD2360 or DD2356. These are the two basic courses that we took some material from. If you want to have an overview of all the topics, including GPU programming, a good textbook covering all the topics is High Performance Computing Modern Systems and Practices by Thomas Sterling, who is a very famous HPC researcher from University of Indiana. So there is an online copy for KTH student available, so you can click on the slides, and keep in mind these are for KTH students, so you need to log in first as a KTH staff, and then you will have access to it. So this book here, it basically gives a very broad overview of all the topics in high performance computing. The second module will be about OpenMP and shared memory programming. This is quite a recent OpenMP book by Ruud van der Pries, Eric Stotzer, and Christian Terboven. Right? So this is a recent book, very, very good, especially covering the new aspects of OpenMP. So when it comes to MPI, there are two main books. So it's the blue book and the green book. So the blue book is basically introduction to MPI, all the basic concepts. Instead, the green one is from using advanced MPI, so all the advanced concepts and all the new stuff that is in MPI. So these books are authored by William Gropp, who is a professor at Urbana-Champaign, from who also I adapted many of the slides that you will see here. But if you're working on MPI code, you want to know more about MPI and how to use in a much more effective way, I would say these are the two books that consider this as as the Bible of MPI. They're also very readable, so I enjoy to read them. It's not just the usual computer science book just focusing on the interface, right? But it discusses applications and deeper concepts. When it comes to GPUs, there are two books. The first one is CUDA for engineers. So this is a very good book, especially if you're coming from the application side. So you are an engineer, you are a physicist, you are a biologist, you want to use GPU. This gives you the right approach to tackle GPU. However, if you are a computer scientist, you might want to look at programming massively parallel processor by David Kirk and who are two major person in GPU programming. So the first one is more if you're coming from the application side. If you're a computer science scientist, I suggest you this second book that goes more into the detail of the computer architectures and more advanced features for optimization of GPU programming. How is going to happen interaction in this course that is going to be online? So we will try to do our best to interact as much as possible. So the best way to have an answer to any of your question or solution to your problem, if we can solve it, is actually to post your question and comments on the canvas, so other people can jump into the discussion, right? Maybe they have the solution. To email me is also okay, but keep in mind that I might be late. So the best solution is if you submit to Canvas, so people as soon as they see it, they try to answer your question. I strongly encourage you to collaborate for the assignments. So make some space in your schedule to organize meetings with your assignment partners, right? To discuss the assignment, who's doing what, if there's something you didn't understand, and so on. So rely on to work with other students in an effective way. Also, I will organize some Zoom calls just to touch base with you, basically at the beginning of each module, to check basically if there is any major problem or question that you want to bring it in. So how the preliminary agenda looks like. So we are going to look at the benchmarking, performance model, HPC architecture until basically September 13, where the first assignment is due. We switch to shell memory programming with OpenMP until September 2023. And then we will look at programming with MPI October 4th and GPU architecture by October 21st. Keep in mind that by October 23rd, you need all the 4 assignments if you want to pass the course and get your code, your credits registered in LADOC. So why we're here? So why do we need supercomputers? Well, the reason is that today most of the science is not relying anymore on using pens and papers for doing the calculation. We can still do that, but it's important to realize that so many problems, they don't have an analytical solution, right? So you might simplify your problem as much as you can. You might linearize highly nonlinear equation and find a solution. But many of the problems cannot be solved exactly. So the way actually that computers come in is basically to discretize. You go from continuous description of your equation to discrete description of your equation, and then you solve this discrete equation that corresponds to algebraic equation using supercomputers, right? So supercomputers are very, very good to make in parallel many of these calculations of this algebraic equation, right? So even simple problem like to predict the trajectory of 3 bodies that are interacting by a gravitational force is actually a problem that cannot be solved analytically. So this is something that you need some numerical technique. So here in the slides I have this wonderful book, The Three-Body Problem by Chi-Hin Liu. Is talking about the three-problem, right? But also is touching about the concepts of parallel computing. So if you haven't read it, I strongly suggest you to read it. Is an incredible lecture, an incredible reading. So it's also important to understand that what you learn in this course can be applied to a very broad range of science and engineering disciplines. So for instance, some of you might have heard of using GROMACS for molecular dynamics or LAMPS. So the workforce for any weather forecast prediction is a HPC system. So all the weather forecast that you see on TV or you listen to into the radio is coming basically from simulation on supercomputer. Also astrophysics, and try to answer a question about our universe is today is basically relying on the HPC system. So astrophysics, astronomy, space weather, and Earth science. So we also in this strange situation with the pandemic or the COVID-19. So HPC system may also be used in the health sector to predict how infection propagate across people. And of course, some of you probably already work on quantum mechanics code for predicting the materials properties and some life science problem. So, of course, some of the problem that probably you've been working on are solvable on laptop, your workstation. With the supercomputer, we are looking at problem size that are typically problem size that you cannot solve on your laptop. This means that the problem requires a huge amount of memory, much more than the one that you have available on your system. Right? So let's say that you're doing some CFD simulation with the NAC 5000 code. That means that you're going to solve the PD simulation using Poisson like solvers or Navier-Stokes solvers. So the problem size we are talking about here is a problem size of 10 to the 10 nodes, right? So that is also roughly 2000 to the cube. That means that you have 2000 cells in one direction, 2000 cells in the other one, and 2000 cells in the third direction. Also, this is in a structured mesh, so it's kind of irregular meshing. So when it comes to molecular dynamics, especially about particle cells and by problems, also the number of particles might go up to very large number, especially for particle cell. So 10 to the 8, 10 to the 10 is quite common, right? So these are numbers that we cannot handle with a laptop or even a powerful workstation in the lab. So we need to rely on HPC system. So the common theme for this course is use as simple as possible models of computation to gain insight into performance issues. So this insight on expected performance can give a tool to both diagnose issues and to design the performance, that is, optimize the performance of our code. So let's see an example. So we have two codes here. So one is a code that we call blue, and then we have a code that is red. So what we are talking about here is the parallel speed up, and this is the so-called scaling plot. Scaling plot is a plot that has a process, the number of processors that we are using. So you might think as the number of cores on the x-axis, and then here is the speed up. That means that if we have one code, right, and we use more resource and we halve the execution time, just increasing the number of cores, that means that we're having a speed up of 2. So we are able to speed up our code by a factor 2. So you see that here, so the blue line, the speed up, that is relative to the performance of the serial. So when we use only one processor, is much better than the red one. You see that the red is actually flattened out. So the ideal speed up is basically a straight line, right? So it means that if you double the number of cores of the processor, then you basically half the execution time. So the blue line, according to this plot, is and the blue algorithm is much better according to this speed up plot. But the question I have for you, which one is the best? Well, what we need is also another plot in these slides. So here we have the total execution time, right? As you can see here, the total execution time for a small number of processor is actually very high. So that means that if this is the red one is 1, this is so this is 0.1, so this is 1. So this factor of basically of 10 difference, right? It was hidden by the speed up plot that we saw before. So so whenever you read the paper about HPC and application in HPC, you need to be very, very careful, what is shown, because it could be clearly misunderstood. So here you can clearly see that the blue algorithm, that is algorithm 1, has a very poor uniprocessor, unicore performance, while the algorithm 2 has a very good performance. However, the increase that you get by increasing the number of cores is actually lower. So during this course, we will discuss a lot about this, how to show performance, how to discuss the performance, and what is performance good and what is performance is bad. So how do we know if there is a performance problem? Well, for instance, if you are one of the team that you develop the blue code, you will say, well, my code scales well. So the real question we might have is, how actually is efficient, right? So making a unicore scalar code more efficient has the drawback that the decreases on scalability, right? So typically code that scale very well, they don't perform very well on one core. So the question that we will try to address in this course is, how can we know to what we do compare, right? So in this course we will develop techniques to answer these questions and to guide in the development of HPC code. So this was the last slides. In the next lecture we will start with the first module that is about performance model, benchmarking, and HPC architecture that we need to know in order to exploit them for high performance code. So talk to you soon.